Hello everyone! In this lecture, we will begin to study smart cards and take a closer look at the Estonian ID card. So let us begin. So what is a smart card? A smart card is also known as a chip card or an integrated circuit card. It contains protected non-volatile memory and a microprocessor. So if we take a look at these smart card chip contacts from the other side and zoom in, we can see that a microcontroller is soldered to the contact pad. And if we zoom in even more, we can actually identify some components. There is the CPU, random access memory, read-only memory, and persistent read-write memory, such as EEPROM or flash. So it is basically a computer, but a computer with specifications from the late 80s. For instance, the random access memory in today's chips is only a few kilobytes. If a card has 2 kilobytes of RAM, that is already quite a lot. The hard disk or the persistent read-write memory on these chips may be around 200 kilobytes, and the CPU has computing capabilities as those from the late 80s. What is important is that these chips usually have additional special-purpose cryptographic coprocessors which can perform mathematical operations such as modular exponentiation very quickly. So some operations can be performed relatively fast on these chips. There are only 4 major companies in the world that produce such security chips. These are NXP, Infineon, STMicroelectronics, and Samsung. Everyone else in the smart card business creates their smart card products by writing software for these chips. Some aspects of a smart card are standardized by this ISO standard that defines location of the contacts, electrical interface, the transmission protocols, and so on. So the physical characteristics and the electrical communication protocols are standardized. Then there are different form factors, as you can see here, for the plastic to which the chip is attached. As for the types of communication interface, there are contact smart cards, which we will work with in this course, but there are also contactless cards, the main difference being that instead of contacts, the chip is connected to an antenna that is usually built into the plastic, and it is possible to communicate with the chip using radio waves. And then there are also dual interface cards, which have both a contact pad and a built-in antenna, so that it is possible to communicate with the chip using both interfaces. Let's look at smart card communication. So how can we as software engineers communicate with the card? Data to and from the card is sent using the so-called APDU or Application Protocol Data Unit. An APDU is simply a sequence of bytes with a specific structure, which we will see in a moment. Communication with smart card follows a command-response protocol, similarly to HTTP. The terminal sends an APDU command to the card and the card responds. Here, the card cannot initiate communication with the terminal on its own. It is the same as in HTTP. The client or terminal asks and the server or card responds. So what does a command APDU look like? A command APDU has the following structure. Essentially, there is a mandatory 5-byte header plus optional data up to 255 bytes. The class byte is usually 0. The instruction byte indicates the type of command we are sending, and P1 and P2 are parameter bytes specific to that instruction. Then LC or length contained specifies how many bytes of command data will follow and then follows the data itself. LE or length expected is used to specify how many bytes the terminal expects to receive back from the card. We can distinguish between 4 APDU cases. Case 1, when we do not send any command data, then the 5th byte is absent, meaning that it has value 0. Case 2, when we do not send data but expect 255 bytes in return, so this byte is FF here. If we specified 00 here instead, it would mean that we expect 256 bytes. So in case 2 APDU, 0 means 256. Case 3 is when we send 2 bytes of data. So here length contained is 2, and here are the 2 data bytes that we are sending. And case 4, when we send 2 bytes and also expect some data back, but in this case, LE, length expected, may or may not be sent to the card depending on which transmission protocol we are using. So as you can see, there is some ambiguity. For example, in case 1 and case 2, it is not immediately clear whether the 5th byte here is length contained or length expected. This means that the card has to determine which case it is based on the type of command specified in the instruction byte. So this is how a command APDU looks. The response APDU is a bit simpler. It contains up to 256 bytes of response data plus a 2-byte status word, which indicates how the response should be interpreted. Here are 2 example response APDUs. If we get only 2 bytes, we know these are the status bytes. If we get more, then we know that the 2 rightmost bytes are the status bytes and everything before them is the data. The status code 9000 in hex means that the command completed successfully. Other status words describe various error conditions, and usually data is present only if the status word is 9000. But at this point, you might have a question. Are these command and response APDUs somehow standardized? Well, it depends. Standard commands are used in standardized smart card solutions. The 2 most popular smart card use cases are probably SIM cards used in mobile phones and smart cards used to implement payment cards. Since we want a SIM card produced by one manufacturer to be usable in the phones produced by any other manufacturer, the APDU commands exchanged must be standardized, and the same applies to payment cards. So the commands used in these solutions have to be standardized. Here you can see a table of commands that are used in SIM cards, payment cards, and in other smart card related standards. For example, read binary, read record, update record, create file, and so on. A proprietary product that does not need compatibility can ignore these standards and define their own commands, so there is no guarantee that a random chip implements these commands or that if it does, they perform the same action. Then there are also somewhat standardized status words. Status words starting with 9 in hex mean that the command completed successfully. Other values represent some kind of error, for example, file not found, record not found, and so on. The same status word can have a different meaning for different commands, and that is quite common because the number of values that can be encoded in 2 bytes is limited. Then there is the concept of a smart card file system, which describes how logical elements such as files and directories are organized on a smart card. In a smart card file system, the addressable objects are the master file, which is like a root directory, the dedicated file, which is like a directory, and the elementary file, which is like a data file. Inside a dedicated file, there can be another dedicated file, so it is possible to have subdirectories. These file system objects are addressed by a 2-byte file identifier or FID, and the master file has a standard fixed file identifier of 3F00. What is important to note is that there is no ls or dir command to list files on a smart card. So if you find some smart card on the street, you cannot simply list its contents and see what is inside. What you can do, however, is try to brute force this 2-byte file identifier, thereby enumerating all the files and directories on the card. Usually, though, you would need to know what application the chip implements and therefore what objects to expect there. Today, the concept of a smart card file system is somewhat legacy or outdated. In the early days, where smart cards were just memory cards used to store data, this was useful. Modern smart cards, however, are mainly used to perform cryptographic operations, so newer smart card developments, when needed, usually implement only a partial emulation of a file system. To navigate through the smart card file system, the select file command can be used. It is standardized, and therefore it is very likely that this command will be present in this form in any smart card solution where the file system concept is used. Let us see how it works. For example, to change the current selected file to a dedicated file with the file identifier ABCD, we would send this APDU, these 7 bytes, so let us go through them byte by byte. The class byte here is 0. The class byte usually indicates whether this is a standard command or a proprietary command. If the value is 0, it should follow the standard, although that is not always the case. The instruction byte is A4 and it denotes the select file command. Parameter 1 specifies what type of object to select, and there are several options. 0 means the master file, 1 means a dedicated file, 2 means an elementary file, and 4 means a card application or chip applet. The idea here is that a smart card can contain several applications created by different entities. So using this select file command, we can switch between the applications. For example, an ID card could also have a payment application installed, and then we could use our ID card to withdraw money from ATMs or pay in a shop. Technically, that is possible. In that case, the terminal in a shop would have to explicitly select the payment application using the select file command with P1 set to 4, and this is actually what payment terminals do in practice. After a card is inserted, they try to select Visa and MasterCard chip applets, which have standardized applet identifiers. Parameter 2 specifies the type of response we want. If we specify 0, the card will return the object description. This is some kind of metadata about the object. 04 and 08 include only a subset of this metadata. And 0C requests that the object simply be selected without returning any metadata, and this is what we will use most of the time. LC, or length contained, specifies the length of the file identifier. Usually it contains the value 2, because the file identifier is 2 bytes long, unless it is an applet identifier, which can be much longer. When selecting the master file, we can omit the file identifier, because its file identifier is fixed. The data field contains the file identifier of the elementary file or dedicated file that we want to select, or it can contain an application identifier for selecting applications. As you can see, in our case, it contains ABCD. So this is how we can use the select file command. An important feature of smart cards is the so-called answer to reset, or ATR. These are bytes returned by a contact's smart card on power up, conveying information about the parameters proposed by the card. So when we insert a smart card in a reader and the power is supplied to the card, the first thing the card does is send its ATR to the terminal. Here's an example of an ATR. We can run the command PCSC scan to see the ATR of the card that is inserted in the reader. The ATR is divided into 2 parts. The ATR prefix, which you can see here, conveys the parameters needed to establish an electrical connection to the card. So these bytes here encode a clock frequency, transfer speed, delays, and so on. The other part of the ATR is optional and is called the historical bytes, which you can see here, and they can contain arbitrary data. Usually, the historical bytes are used to identify the card. For example, these are the historical bytes of the Estonian ID card, and they encode the ASCII string EID. Earlier versions contained the string EstEID together with a version number. This tool comes with a database of known ATRs in this file here, and it looks up the ATR and shows that, for example, this ATR corresponds to an Estonian ID card. Note that some cards can return 2 different ATRs. The so-called cold ATR when power is supplied to the card, and the so-called warm ATR when a reset signal is sent, which basically performs a kind of soft restart of the card. Let's take a look at the transmission protocols. There are 2 standard transmission protocols, T0 and T1, that can be used to transmit APDUs between a terminal and card. Let us start with T0. T0 is the simpler of the 2 protocols. It is a byte-oriented protocol, meaning that individual bytes are the units transferred between the terminal and the card. Because it is simple to implement and has low memory requirements, it is widely supported by SIM cards and payment cards. Here is how it works. The terminal first sends the 5-byte APDU header, and the card responds with a procedure byte. This procedure byte can indicate one of 2 things. It can contain an acknowledgement value indicating that data transfer can continue, or it can contain the first byte of the status word, signaling that the second byte of the status word will follow without any further data transfer. So here, the card can return a status word without receiving any data from the terminal. This allows the card to decide whether to receive data from the terminal based only on the APDU header it has received. Another important point is that both parties must know in advance in which direction the data will be sent, because the same procedure byte acknowledgement value is also used by the card to indicate that the card will start sending data. If both sides wait for data, the exchange times out. If both sides send data at the same time, the exchange fails. Therefore, the data direction has to be determined by the APDU command itself. For example, one type of commands may be used to send data to the card, while another type to read data from the card. Also note that the data sent or received must be exactly P3 bytes long, because the P3 byte is used by the receiver to determine when the sender has finished transmitting the data. So in the T0 protocol, the P3 field serves either as length contained or length expected, depending on the direction of the transfer. So the main limitation of T0 is that in one round, data can be transferred in only one direction. So we cannot both send data and receive data using a single APDU request-response sequence. To return data when the terminal has also sent data, the following workaround is used in the T0 protocol. Let us say that the terminal sent an APDU containing data, but the card also wants to return some data to the terminal. In this case, the card responds with a status word where the first byte is 61 in hex, and the second byte specifies how many bytes the card wants to return. The terminal is then expected to send the getResponse command, like this. Here, C0 is the instruction byte for the getResponse command, and in parameter 3, or length expected, the terminal specifies the number of bytes the card wants to return. The card then returns those bytes together with the status word. So in order to both send and receive data for the same logical operation, an additional APDU command is used. The card first indicates how many bytes are waiting, and then the terminal retrieves them using getResponse. To fetch data larger than 256 bytes, several getResponse commands can be sent in a row, in which case the card again returns status word 61, and this process is repeated until all the data that the card wanted to return has been sent. Another workaround for retrieving data when the terminal does not know how many bytes the card has is to send an APDU with an incorrect length expected value in parameter 3. So if an APDU contains an incorrect length expected value, the card responds with a status word where the first byte is 6C and the second byte specifies the correct number of bytes available. The terminal can then resend the same command, but with length expected set to this value returned in the status word, and the card will now return those bytes together with a new status word. As you can see, here again we need two commands, because the T0 protocol does not provide a mechanism for transmitting an amount of data different from what is specified in parameter 3 of the APDU header. So these are the limitations of the T0 protocol, but they are addressed by the improved T1 protocol. A T1 is a newer transmission protocol that was standardized more recently, but it is more complicated and is not supported by all smart cards. T1 is a block-oriented protocol, meaning that here the APDUs are encapsulated in blocks forming Transport Protocol Data Units, or TPDUs. So here is how it looks. Basically, an extra protocol layer is added with a header and a footer, and here is what these fields contain. NAD specifies the node address, but this feature is not used in practice. The idea was that it would be possible to open several parallel logical channels to the card, and this field would then specify to which logical channel the TPDU should be sent. But this feature has not been popular. PCB contains the protocol control byte, which specifies what type of block it is. In this case, the block carries APDU data, but it can also be a block that carries an error message, for example. Len tells us how many bytes of data the block contains, then comes the data, in this case the command APDU, and finally the CRC, which is a check value used for error detection. The same fields are also present in response APDUs. As you can see here, in one round, data can be sent in both directions, because the request and the response each has their own length field. This also means that technically the actual amount of APDU data sent and returned may differ from the values specified in the command APDU's length contained and length expected fields. This fact may be easy to overlook compared to the T0 protocol. A T1 supports a feature called Extended APDU, which allows up to 65,000 bytes to be sent in a single APDU. The data can be split across several TPDU blocks and then reassembled by the recipient. T1 also provides more advanced error detection and handling. In the T0 protocol, a parity bit was sent after each byte transmitted over the wire in order to detect whether the byte had been received correctly. Here, there is the CRC field, and there are also specific error messages that can be sent by the communicating parties. So a smart card can support T0, T1 or both protocols, and the good news is that the same APDU can be sent over both T0 and T1, except for sending extended APDUs, which is available only with T1. Therefore, to write code that works with both transmission protocols, just make sure that the extended APDU feature is not used, and that the code is able to handle the two status words that are specific to the T0 protocol. A bit about electrical communication to give you an overview of how things work at the electrical level. So the contact pad of the chip has these 8 contacts. The VCC and ground contacts are used to supply voltage to the chip. The chip does not have a built-in power source, so it relies on the terminal to supply power. There are 3 voltage classes: 1.8, 3 and 5 volts. A chip does not have to support all, but it must implement protection so that it is not damaged if a higher voltage than the one it supports is supplied. Most modern chips use 1.8 or 3 volts because a lower voltage also means lower current consumption, which is important for devices such as mobile phones since we do not want a SIM card to consume too much of the battery. Then there is the reset contact through which a reset signal is sent to boot or restart the card. The input-output line is the most interesting one because this is where the actual data, the APDU bytes, is sent back and forth. It is synchronous, meaning that data can flow in only one direction at a time. The clock line is used to supply a clock signal to the chip, which is needed for the card and terminal to synchronize the data transfer speed. The standard defines a range from 1 to 5 MHz, but the readers I have seen in practice usually supply a clock signal of 4 to 5 MHz. It is interesting to note that for older cards, the clock signal was also used to clock the card's CPU, so the speed of the card was proportional to the clock signal generated by the terminal. Newer cards for a CPU use a built-in clock generator, so for these cards, the CPU speed is fixed. Now, these 3 contacts are not connected to the chip. C4 and C8 are reserved for future use, while C6 was used for older technology cards that required a higher voltage from the terminal to update the card's internal memory. If you are interested in sniffing the electrical communication between a card and reader, it can be done quite simply and cheaply. What we need is a device called a logic analyzer. For example, in this picture you can see the SALI USB logic analyzer, which is able to analyze 8 channels in parallel, supports a sampling rate of up to 24 MHz, and costs around $220. A logic analyzer is a simple measurement device that detects whether there is voltage on a wire or not, but it does this very quickly. This analyzer can perform 24 million measurements per second and will send a bit 1 to the computer if there was voltage and 0 if there was not. As you can see, it has 8 wires, so it can sniff 8 connections in parallel. This logic analyzer is quite expensive, but you can buy a Chinese clone on eBay for only €6. In fact, the device shown on this picture is the cheap clone. Then we need to connect the logic analyzer to wires. The I/O line where the data is transmitted, VCC, which is the power line, the reset line to sniff the reset signal, and the clock line to synchronize the data transfer. This is the screenshot from the software that comes with the logic analyzer. It is possible to set a trigger for data capture. For example, we can specify that as soon as there is voltage on the power line, the tool starts capturing data. And this is what we will see as the output from the logic analyzer after inserting a smart card into a reader. First, voltage is supplied to the chip, and at the same time the clock signal is applied. This continuous white block means that the clock signal is changing very quickly. Then, to start booting the card, the reset line is raised, and on the input-output line, we can see some bytes. This here is the first byte of the ATR, and these here are the remaining bytes. As you can see, there is some delay between the first and the others, probably because the value of the first byte is hard-coded, while the remaining bytes are stored somewhere in memory and have to be fetched, which results in a delay. If we zoom in on the clock signal, we can see that the voltage changes very quickly at 4 MHz, that is 4 million times per second. Then if we zoom in on the input-output line, we can see how the ATR bytes are transferred bit by bit. For example, this here is 0, 0, then 1, 0, 1, and so on, each byte being transmitted using 9 bits, the last one being a parity bit. So, as you can see, the electrical communication protocol of smart cards is quite simple, as we can even read the values of APDU bytes visually. But we can also use the built-in serial analyzer, and after specifying the correct bitrate, it will decode the transmitted byte values. So here you can see the 5-byte command APDU header, here the status word of the response, and here you can see the delay, showing how much time it took for the card to process the command and produce the response. So, using a logic analyzer, we can sniff any communication protocol at the electrical level, perhaps even a USB interface, although USB 2.0 would already be too fast for this particular logic analyzer. We would need something with a higher sampling rate, but I hope you get the idea. Let's look at the Estonian Electronic Identity Card, abbreviated as EstEID. The Estonian ID card is an identity document issued by the Estonian state. Actually, there are several different types of identity documents that we refer to as an ID card. There is the identity card, which you see here, but there is also the residence permit card issued to non-EU nationals, the diplomatic identity card issued to diplomats and their family members, and the digital identity card issued to e-residents. These identity documents provide the same electronic functionality, only the appearance of the cards differs slightly. So each of you should hold one type or another of the Estonian ID card. Why this card is interesting to us is because the smart card chip contains 2 asymmetric cryptographic key pairs and the corresponding public key certificates. Here the smart card chip performs the function of an HSM or hardware security module by securely storing the private keys, performing cryptographic operations internally, and returning only the result. The Estonian ID card is probably the most successful electronic ID card deployment in the world in terms of both deployment and actual usage. The card can be used to securely authenticate to remote servers, to create qualified electronic signatures, and to decrypt documents. So the Estonian ID card is a very good example of a nationwide PKI. The subjects are Estonian residents as well as so-called e-residents, people who do not have a residence permit in Estonia but who want to use the electronic functionality of the card. The certificate authority, which in EID's terminology is a qualified trust service provider, is SKID Solutions for previous generation cards, but ZS Estonia for the latest cards. The certificate authority has delegated identity verification to the registration authority, the Police and Border Guard Board. The task of the police employees is to verify that the ID card and certificates are issued to the rightful owner. The manufacturer for the first generation cards was Gemalto, the previous generation cards were manufactured by Idemia, and the latest generation ID cards shown in this picture are manufactured by Thales. Here you can see the manufacturing line for Gemalto manufactured ID cards. What is important to note here is that the ID card manufacturer personalizes the cards and generates the key pairs. We cannot generate the private key ourselves. So here we have to trust that the manufacturer generates the keys securely and does not create copies of our private keys. For security reasons, the keys are generated on card by the key generation algorithm built into the chip, in order to exclude the possibility that copies of the private key could exist outside the chip, which is nice in theory but not always so in practice. Some years ago, there was a scandal because it was discovered that the ID card manufacturer, Gemalto, in some cases had generated the keys outside the card and then copied them onto the card. In a few cases, even copying the same key onto multiple ID cards, which allowed cardholders to impersonate each other. This malpractice was discovered by yours truly, and the details of how it was discovered and proved are described in this paper and summarized in this 10-minute video presentation. The Estonian state took Gemalto to court, and later a compromise agreement was reached, with Gemalto paying compensation to the state. Now, the unofficial explanation was that the keys were generated outside the card to speed up the card personalization process, because the RSA key generation algorithm used by the card was quite slow. As in the worst case, it could take several minutes to generate a key. For elliptic curve cryptography, key generation is much faster, because there the private key is just a random number and the public key is obtained by performing a single elliptic curve point multiplication. So for ECC, on-card key generation is not a performance issue, and the current ID cards are using ECC keys for the key pairs. So what precisely is the electronic functionality provided by the chip of the Estonian ID card? The two most important objects stored in the chip are two 384-bit elliptic curve key pairs. One is the authentication and decryption key, and the other is the digital signature key. These keys cannot be read out, but we can perform cryptographic operations with them. The card also stores the corresponding X5N certificates, which can be read from the card without any authentication. Then there is pin 1, pin 2, and the PUK code verification mechanism. Pin 1 must be entered to perform operations with the authentication key, pin 2 to perform operations with the digital signature key, and the PUK code can be used to change or unblock pin 1 and pin 2 codes. So together with the ID card, the cardholder also receives a PIN envelope in which these PIN and PUK codes are printed. To prevent PIN brute force attacks, a retry counter is maintained for each PIN. It is decreased after each incorrect PIN entry, but reset after a successful authentication. For the ID card, this retry counter is set to 3. So the code becomes blocked if it is entered incorrectly 3 times in a row, similarly to SIM cards and payment cards. Then there is a publicly readable personal data file which contains the same data as is printed on the ID card. Previous generation ID cards had 15 records, while the latest generation ID card has 23 records in the data file. Then the older generation cards have key usage counters, which show how many times cryptographic operations have been performed with the authentication and digital signature keys, and these counters are publicly readable. For example, here you can see in the Digidoc application under the My EID tab that the authentication key has been used 214 times and the signature key has been used 56 times. So these counters can be used to determine how much the cardholder uses the card electronically. Not too useful perhaps, and that may be the reason why these counters are no longer available on the latest generation ID cards. Then there are so-called card management keys, which can be used to perform card management operations. These are symmetric keys which are installed on the card during the card personalization phase, and they allow the card issuer to establish an end-to-end encrypted and authenticated channel to the card and perform various card management operations. One example is resetting or overwriting PIN codes. So if we forget our PIN codes, we can go to a police office and get a new PIN code envelope. The card management keys will be used to establish a secure channel with the card, new PIN codes will be written to the card, and we will get a new PIN envelope. This feature, however, is no longer supported on the latest generation ID cards. Instead, it is possible to log into the ID card administration portal using, for example, Smart ID and view the card's PUK code, which cannot be changed. The card management keys can also be used to replace certificates or to even generate new private keys. Then, using the chip-level keys, it is even possible to reinstall applets or install additional smart card applets on the card. We will look at this functionality in the next lecture. Now, about the Estonian ID card chip platforms. Over the years, several smart card chip versions have been used to implement the required ID card functionality. So let's take a brief look at each platform. The first Estonian ID card was built using the Micardo platform. This is how the card looked, and this platform was used for 9 years, from 2002 to 2011. The Micardo operating system provided a limited but quite flexible configuration. For example, you could create key objects and pin objects, specify access rights to read and write files, performing cryptographic operations, and so on. So this is when the creators of the Estonian ID card decided what functionality the card should provide. Up to now, all later ID card platforms have continued to provide the same functionality. Then, in 2010, a digital identity card was introduced. As you see, this identity document is not meant for physical identification as it has no photo, so it serves only an electronic purpose. And today, such digital identity cards are issued only to e-residents. The card used the Maltos platform, where smart card applets are written in a programming language similar to C. So someone wrote an applet that implemented the same functionality as the Micardo card, mimicking the same commands and responses, emulating the necessary files, and so on. Now, these two platforms supported only 1024-bit RSA, which is considered insufficiently secure by today's standards. Then, in 2011, a major change took place. A new platform and a new ID card design were introduced, the chip was moved to the back of the card, and new physical anti-forgery security features were added. This was a Java card platform, meaning that there is a tiny Java virtual machine on the card that can run Java applets. Again, someone wrote a Java card applet that implemented the same interface as the two previous platforms, but this card was more powerful because it supported 2048-bit RSA. In autumn 2014, there was an upgrade from the SLE66 to the SLE78 platform, and this SLE78 platform turned out to have that notorious Infineon RSA key generation flaw, which led to the ID card crisis in 2017. The fix in that case was to switch from RSA to ECC keys. Then, in December 2018, the IDEMIA ID card platform was introduced. A new design and new security features were added, the most noticeable one being the color photo. This is also a Java card, but it runs the internationally standardized European Citizen Card applet. It is configured to provide the same functionality, but the interface is quite different. So while the first generation cards implement the same communication interface, this card uses slightly different APDU commands to provide the functionality. The switch from self-made applets to this European Citizen Card applet was made because this applet had passed expensive security certification, which is now required under the eIDAS regulation. So this platform is the first one to have received extensive security testing. The applets installed in the earlier cards had not been security certified and had not even been sufficiently audited, which led to security incidents. For example, it was discovered that the ID cards issued in 2011 had a pin bypass vulnerability, which is described in more detail in this report. The exploit involved sending a very long APDU, thereby overwriting the Java card APDU buffer where the vulnerable applet stored the pin verification status flags. At that time, this incident was not publicly disclosed, and these details became public only 10 years later. Anyhow, in November 2025, the latest generation ID card platform was introduced with a new design and new security features. Functionality-wise, this platform is similar to the previous generation ID card platform. Today, cards based on these earlier platforms have expired, and only cards based on these two are in use. These last two platforms are dual interface cards, meaning that we can interact with the chip also over the NFC interface. However, for privacy reasons, the APDU data must be encrypted using this 6-digit password printed here. So for these cards, you should consider hiding this code unless you want someone to be able to communicate with your ID card over the contactless interface. Here are links to two EstEID specifications. This specification covers the communication protocol implemented by the previous generation IDEMIA platform, while this one covers the latest generation Thalys platform. The specifications are in English and contain examples of how to communicate with the card. To implement the homework, you may need to consult one specification or another depending on which generation ID card you have. So the communication interface is publicly documented, while the software running inside the card is closed source and proprietary. Let's move to the hands-on part and discuss how to set up the hardware and software needed to communicate with the smart card. First, get yourself a smart card reader. There are several popular smart card readers available in Estonia. The OmniKey Cardman reader is a popular option and costs around 15 euros. Then there is this very handy reader called the smallest smart card reader. The good thing about it is that you can fold it and keep it in your wallet because it is very small and has no wires. Another important reader to mention is the Gemalto ID Bridge reader, which is the most secure option because it contains a pin pad where you can enter the pin. The pin entered here does not go to the computer but is sent directly to the smart card. So if your computer is infected with malware, the malware cannot learn your pin codes. Now, if your laptop already has a built-in smart card reader, you can use that, but previous experience shows that built-in readers may have issues, so be aware of that. We have quite a few OmniKey readers. If you need one, we can lend you one. Now, once you have a reader, plug the reader into a USB port. Then, if you are using VirtualBox, forward the USB device to the guest OS, which in our case is Ubuntu. For USB support, you may need to install the VirtualBox extension pack. It has been observed that if you have a Windows host and you have installed the USB backup program that comes with Wireshark, it may prevent USB devices from being redirected to the guest OS, so make sure to uninstall it. Add a USB filter if the host OS fails to release the USB device. In some cases, the host OS will start using the attached USB device and will not release it when you try to redirect it to the guest OS. This is a common problem on Windows hosts, and the workaround is to create an empty USB filter, and after the filter is created, any new USB device attached will be automatically redirected to the guest OS, bypassing the host OS. Check whether the smart card reader is detected by Ubuntu. Here you can run the dmsg command, and at the end of the output you should see that a new USB device has been connected. Running ls-usb should show you the connected USB devices. Here you see the external USB reader, and this is the reader built into my Dell laptop. On most laptops I have seen, the built-in reader is powered on only after a smart card is inserted into the reader. So make sure to insert a smart card before testing a built-in reader. About the software. From the Ubuntu packages, install PCScd and PCSE tools. PCScd is a service that accepts commands from user space and sends them to the smart card readers connected to the system. Make sure to start the PCScd service if for some reason it has not started automatically. Then, if you run PCSE scan, you should first see the card readers detected by the middleware and then their status. You can see that this reader does not have a card inserted, but this reader has a card with this ATR. To send APDUs using Python, we have to install the PyScard Python module. Then we can run Python, import the smart card module, and this will return a list of the connected readers. Here we can see two readers connected to the system, and this is how we can establish a connection to the reader with index 1, which in this case is the Gemalto reader. Then we connect, and the getATR method on the connection returns the ATR with which the card responded. So you can see that the ATR is returned as a list containing integer byte values. Then we can use the transmit method to send APDUs to the card, and it will return data and the status words. Here, the data is an empty list, and the status words are 110 and 0, which in hex is 9000, meaning that the command completed successfully. The homework template will contain the following helper code. These lines import the required methods from the smart card library, and this line will wait until a card is inserted into any card reader, and if no card is inserted within 10 seconds, an exception is raised. This line establishes a connection to the card using the T0 protocol. The Estonian ID card supports both protocols, so T1 could also be used here. Then this line prints out the name of the selected reader. These lines retrieve the ATR of the card, and based on the received ATR, print out the type of the card. If the ATR is not recognized, the program will print unknown card and exit. For APDU transmission, the homework template contains a helper function called send, which is basically a wrapper around the transmit method. The send method accepts an APDU as its parameter, sends it to the smart card, and receives the data and the status word bytes in return. If the status word corresponds to success, the data is returned. If the status word starts with 61, it means that the card has additional data to return. The helper function will recursively invoke the send method by returning the response of the getResponse command. The same applies to a status word starting with 6C, in which case the same APDU is resent but with the corrected length expected field. So these are the workarounds for the T0 protocol. If the status word is something else, an error message is printed and the execution of the script stops. This is done to stay on the safe side. If we encounter some unexpected error condition, we simply exit, as it does not make sense to continue our script, because if one APDU command has failed, all the following commands that depend on it will most likely fail as well. It is important to note that APDU commands and responses are lists containing integer byte values. For pretty printing, a list of integers can be converted to hex string using this toHexString function, which we imported from the smartcard.util library. So it returns these byte values in hex separated by spaces. To convert a list of integers to bytes, we can simply use the bytes method, as you can see here. Very good, now we are well prepared, let's move to the homework. For this lecture, there are two homework tasks. The first task is EstEID info, where you have to implement a utility that reads the personal data file and the pin retry counters from the ID card. This is the output produced by running the utility with my previous generation Estonian identity card. The utility prints the name of the reader, the name of the card platform, then the contents of the personal data file, as well as the pin retry counters, which show how many attempts remain, where the maximum value is 3. Here is the output for the new generation Estonian ID card, and as you can see, the difference is that instead of 15 records, it contains 23. Your solution only needs to support one ID card platform, either the older IDEMIA generation or the latest Thales ID card generation, depending on which one you have. So how to read the personal data file? For the previous generation ID card platform, you can check the IDEMIA specification on page 30, but here is how to do it. The first step after establishing a connection to the card is to select the applet, because the EID applet is not the default selected applet, and hence we have to select it manually using the select file command and specifying this applet identifier. Then we have to navigate to the specific personal data record file, which has this path. Using the select file command, we first select the master file, then this dedicated file, and then this elementary file, specifying the record number in the second byte of the file identifier. So you will need 3 select file commands to select this path. Once this file is selected, we can use the read binary command to read its contents. Here is an example of how to read the personal identification code. First, select the applet, select the master file, select the dedicated file, and then select the elementary file containing the personal identification code, which is stored in the 6th record. Then fetch the data using read binary and print it out. The characters are encoded using UTF-8. So here you would place these 2 lines inside a loop, only changing the file ID of the elementary file. Now, if you have the latest generation Thales ID card, you can check page 46 of the new specification. The process is very similar. The main difference compared to the previous generation ID cards is that the personal data file records are stored in the document data dedicated file, which has to be selected in a similar way to an applet identifier, and there are also more records available. So this should be quite straightforward. About the pin retry counters. If you have the previous generation ID card, select the master file for pin 1 and PUC, while for pin 2, you have to select this dedicated file under the master file. Then, to obtain the number of remaining pin verification attempts, send an empty verify command in P2 specifying either 1, 2, or 133, depending on which code you want to obtain the counter. Empty here means that the command APDU contains no data. This is important because if you send some data, the card will treat the data as a PIN code and perform authentication, decreasing the retry counter if the PIN is incorrect. So the command data must remain empty. The verify command will return the status word in this form, where the 4 least significant bits of status word 2 contain the number of remaining tries left. So this value x here can range from 0 to 3. And if it is 0, then the PIN code has been blocked and you have to use the official software and the PUC code to unblock it. To access the return status word, you cannot use the helper method send defined in the template. You have to use the transmit method directly and then parse the second byte of the status word. For the latest generation ID card, the process is very similar, but there is no need to select a separate dedicated file for PIN 2, and the PIN code reference values are different. Now, the second task is to implement a utility that downloads the certificates stored on the ID card. The utility accepts the type of certificate, auth, or sign, and the file where to write the certificate in PEM format. It shows the name of the reader and the ID card platform, the size of the certificate in bytes, and stores the downloaded certificate in the file specified as an argument. The OpenSSL tool should be able to parse the certificate successfully. For the authentication certificate, the key usage extension should contain digital signature, while for the digital signature certificate, the key usage should be non-repudiation. If the certificate was downloaded correctly, we should also be able to verify the signature on the certificate. In the certificate's CA issuers extension, we can find the URL of the CA certificate, download it, convert to PEM format, and verify the signature. It should show OK here. If it shows an error, the certificate most likely is corrupted. Please note that this is an example based on my certificate, and your certificate can contain a different issuer, CA here. So how do we read the certificate? You can consult the corresponding EstEID specifications depending on which ID card platform you have, but here is the basic process. First, select the applet identifier. Then, to read the authentication certificate, we have to use the select file command to navigate to this dedicated file and this elementary file, or to this file if you have the latest generation ID card. Note that on the Thales ID card platform, the select file command has a somewhat non-standard implementation, and therefore you will have to select this path with a single select file command using parameter 1 with value 8. You can look at the example provided in the specification. For reading the digital signature certificate, the steps are similar. The certificate is stored in their form in a file of fixed size. So what you have to do first is this. With the read binary command, read the first 10 bytes of the certificate file. Then you have to calculate the length of the certificate by parsing the length bytes of the certificate's outer ASN1 sequence. And the requirement is that all possible their length values must be correctly handled. You cannot hardcode that the length is specified in the byte at offset 5, for example. Your solution has to correctly handle certificates of any size and not just the size of the certificate you have on your card. Then once you know the certificate length, read the entire certificate in a loop using the read binary command. The issue is that with one read binary command, a maximum of 231 bytes can be read from the card. Therefore, you have to read the certificate in chunks, specifying in each command the offset from which to read. The offset is a 2-byte integer. The most significant byte of the offset must be specified in P1 and the least significant byte in P2. So how to do that? An integer I can be split into 2 separate bytes, the most significant byte and the least significant byte, by using these bitwise operations. I really hope that by now you all understand what exactly these 2 bitwise operations are doing here. Another important requirement for this task is to make sure that only the minimum number of bytes are sent to and from the card. Sending bytes to and from the card is a relatively slow process, so your solution must not send excessive commands. If it does, the grade will be penalized slightly. For example, if you already read the first 10 bytes here, then do not read them again in the loop here. Okay, so these are the 2 homework tasks for this lecture, but there are a couple of more topics to discuss, so let's continue. The first topic is authentication using a browser extension. This is a relatively new concept invented by the Estonian state, and it is called Web EID, Electronic ID Smart Cards on the Web. Traditionally, smart card authentication in browsers has been implemented by performing certificate authentication at the TLS protocol level, which we will look at when we study the TLS protocol. In this new approach, authentication is performed at the web application level with the help of a browser extension that exposes JavaScript calls invoking a separate native Web EID application. Here is how it looks from the user's perspective. Let us say we want to authenticate to some website. We click Authenticate. And at this point, the website makes a JavaScript call that invokes the authentication process. The native Web EID application pops up asking us to insert the ID card, and once the ID card is inserted, it asks us to enter PIN 1 to confirm the authentication request. After the PIN code is entered, we are successfully authenticated to the website. Now, what happens in the background is that the website makes a JavaScript call authenticate, passing it a random challenge nonce that must be signed using the ID card's authentication key. This JavaScript call returns the signature together with the user's certificate. The website can then verify the signature using the public key from the user certificate, and if the verification succeeds, authenticate the user. What is important to note here is that what is actually signed by the ID card is not just the random challenge received from the website, but also the origin of the website to which we are authenticating. This origin is basically the address of the website, which is added by the browser extension, so it is a trusted value that cannot be influenced by the website. Binding the signature to the specific website is important from a security perspective because if only the challenge were signed, malicious websites could perform man-in-the-middle relay impersonation attacks. For example, a malicious website could ask us to sign a random challenge that had been generated by some other website and could effectively impersonate us on that other website. Since the challenge here is bound to the website that requested authentication, it cannot be relayed to some other website because the expected value in the origin field would be different and the signature verification would therefore fail. This is what makes this authentication scheme phishing resistant, meaning that the service provider name serves only an informative purpose. It is actually safe for us to confirm such an authentication request blindly on any website without worrying that a malicious phishing website could use it to impersonate us on another website. And this is very different from password authentication or from the Smart ID and Mobile ID authentication schemes, where if the user initiates the authentication process on a malicious website, an attacker can impersonate the user on other websites. The benefit of using this approach instead of TLS authentication is that it is independent of the browser. This allows Web EID developers to provide a consistent authentication experience across browsers while improving functionality and fixing issues without relying on browser vendors. So today, this authentication method is the recommended way to authenticate ID card users. Digital signing using a browser extension is a very popular way of creating digital signatures. Most digital signatures are not created using the DigiDoc application, but are given in a web environment when a website requests us to sign something. Here's an example from online banking. So I have created a payment transaction and now I want to confirm it. To do that, I click here on Sign with ID card PIN 2. Then the browser, or more precisely, the browser extension, asks me to choose the certificate. If I had several ID cards connected, it would show a list of certificates. So after I click the Confirm button, my ID card's digital signature certificate is sent to the service provider, in this case the bank. What happens next is that the service provider prepares a XADE signature structure and in the next step asks me to enter PIN 2 to sign it. An important detail here is that the service provider sends to the browser only the hash value that needs to be signed. So at this point, I have no clue what the actual data is that I am digitally signing. After I enter the PIN code and click Confirm, the ID card produces the signature, which is then returned to the service provider. Then the signature is verified on the server side and the bank returns that payment orders successfully submitted to the bank. Technically, this use case is enabled by a browser extension that exposes two functions that can be called using JavaScript. Function getCertificate can be used by a website to obtain the ID card certificate, and sign, which can be used to obtain a signature over a hash value created by the private key that corresponds to this certificate. So this kind of digital signing through a browser extension is secure for the service provider, but it is not secure at all for the user, because a service provider can trick the user into signing anything without the user being able to see what is actually being signed. This means that this kind of blind signing has questionable evidentiary value, because the main purpose of a digital signature is to prove the intent of the signatory. But how can that be proved if the signatory cannot verify what data is being signed? The correct way to do this would be for the user to download the ASIC container, inspect it, sign it, and then upload it back to the website. But that, of course, would be less convenient for the user, and therefore this kind of blind signing is used instead. And this is a problem not only for ID card signing using a browser extension, but also for digital signing using Smart ID and Mobile ID, as these solutions also do not provide a way to inspect what we are being asked to sign. To summarize, this kind of blind signing is the reason why digital signatures provide very little security in practice. And today, it is secure authentication that actually protects our digital identity. Another topic related to the ID card is the so-called biometric passport, also known as an ePassport or digital passport. The technical term for it is eMRTD, Electronic Machine Readable Travel Document. So what is it? You probably know that passports with this symbol here have a built-in contactless smart card chip. And this contactless smart card chip stores digitally the information that is printed on the data page, including the facial image of the document holder. The image is a JPG file around 20 kilobytes and has a resolution of 400 by 600 pixels. The eMRTD chip is used not only in Estonian passports, but also in Estonian identity cards and residence permit cards. The latest generation ID cards are dual interface cards, which means that the eMRTD applet physically resides on the same chip that provides the eID functionality of the ID card. In the first generation residence permit cards, there was a separate contactless chip that provided the eMRTD functionality. So previously, the eMRTD and eID applets resided on separate chips. Now, what is neat about the whole concept is that the personal data in the eMRTD applet is digitally signed by the country that issued the identity document. So there is an international PKI with each country having its own signing certificate authority. The idea is that the authenticity of the document can be verified by checking the digital signature on the data. So instead of relying on a human to verify the physical security features of the document, this cryptographic check can be performed very reliably by a computer in milliseconds. So here cryptography is used to prevent forgery. The idea is that forging a digital signature should be much harder than creating a physical forgery that must be detected by the human eye. Now, to provide some privacy, the data from the eMRTD applet can be read only using a key derived from the machine readable zone, or MRZ, which is these lines here, or by using a 6-digit card access number printed here. The key derived from the MRZ consists of 3 concatenated values: the document number, the date of birth, and the document expiry date. Using these MRZ values or the card access number, a secure channel can be established with the applet and the data then be read from it. So usually the machine readable zone is parsed using OCR or optical character recognition, and then the contactless reader establishes a secure connection to the contactless chip and reads all the data. As an additional security feature to prevent cloning of a document, there is also a clone detection mechanism based on a private key stored on the chip. Each document stores a unique private key with a corresponding public key signed by the document issuer. This private key cannot be extracted from the chip. To verify that the chip contains the expected private key, the terminal can send a random challenge that must be signed using the private key. An alternative mechanism is that the terminal and the chip run a cryptographic protocol in which the chip proves to the terminal that it has access to the corresponding private key. If there were no such mechanism, it would be trivial to clone an eMRTD chip by simply copying this digitally signed data to another chip and obtain an electronic copy of the document. Now, as a rule, the fingerprints of the document holder are also stored on the chip, but since fingerprints are considered more sensitive biometric information, the terminal has to prove to the chip that it is authorized to read them. So, reading fingerprints requires terminal authentication, and here is how it works. Each terminal has its own private key, and if country A wants to authorize biometric data reading by terminals from country B, then country B provides the public keys of its terminals to country A, and country A issues public key certificates for those terminals. The chip will disclose the fingerprints to a terminal if that terminal can present a valid certificate and prove that it has access to the corresponding private key. So, for terminals of friendly countries, the Estonian state would issue certificates so that those terminals could read fingerprints from documents issued by the Estonian state. But what if a key from a friendly terminal is stolen by an unfriendly country? So there has to be some revocation mechanism. What is used in practice is short-lived certificates. Certificates with a short validity period, so that if a terminal is stolen, the attacker can use it only for a limited amount of time. Now, the problem is that the chip does not know the current time because it has no built-in clock, and therefore it is problematic for the chip to check whether the certificate has not expired. To keep track of the current date, the chip remembers the most recent certificate issuance date among the certificates it has seen during terminal authentication. In that way, it knows at least a lower bound for the current date. This is not perfect because it works only if the document is used frequently in terminal authentication. Otherwise, the most recent date seen by the chip becomes outdated, and terminal authentication with expired certificates may become possible. And of course, it is also important here that the CA never issues a certificate with an issuance date in the future, because then all other certificates with the correct issuance time would be rejected as expired. So, revocation for terminal authentication is not that trivial. By the way, a fun fact is that in the first generation Estonian residence permit cards issued starting 2011, the fingerprints were not protected at all, because they could be read over the contactless interface without any authentication, not even using the key derived from the machine readable zone. The protection was introduced only at the end of 2014 for the second generation cards. So these fingerprints that you see here were downloaded from one of the cards where they were not protected. Now, the functionality provided by these electronic machine-readable travel documents enables the possibility for automated border control, or e-gates, meaning that border control can be performed by a machine. To verify that the person presenting the document is its rightful holder, facial recognition technologies can be used, or alternatively, fingerprint scanning, although this is not common as it requires terminal authentication. Here is an example of how e-gates work in practice. Once the passport is placed on a reader, the machine-readable zone is scanned, a connection to chip is established, and the digitally signed data is downloaded and verified. Then the first gate opens, and to open the second gate, the facial verification process has to be completed. After moving the head into the correct position, the face verification process is completed successfully, the gates open, and we can enter or leave the country. Now, in practice, this process still has to be supervised by a human, as otherwise the facial verification process could be tricked by showing the camera a photo of another person. These systems use various liveness detection heuristics, but there are also various attacks that can be used to bypass them. A human is also needed to carry out manual inspection in case the technology, for some reason, fails to recognize the document holder. Now, to summarize, physical identity documents are increasingly relying on cryptography to prevent forgery. This reduces the risk of physical forgery, but creates dependence on PKI and cryptography. And as we have seen, there are many ways in which things can go wrong. For example, if a country's CA private key is compromised, perfect ePassport forgeries can be produced quite easily. As the use of this technology grows, we will see how well it holds up in practice. In this course, we will not communicate with smart cards over the contactless NFC interface, but if you were wondering how this is done, there is really not much difference. We simply have to use a contactless smart card reader such as this one. This is the ACS ACR USB NFC reader, which costs around 30 euros, and it is a very popular reader because it is quite cheap compared to other NFC readers. Contactless smart cards operate over a frequency of 13 MHz, according to this ISO standard. There are two types of cards, those that implement Type A or Type B communication. The difference lies in the modulation method and the anti-collision techniques used. And there is really no preference here, both types of cards are popular. For contactless cards, we do not use the term answer to reset, but instead the term answer to select. It can also contain historical bytes, but it is constructed differently from the ATR used for the contact interface. The name of the transmission protocol is T=CL, where CL means contactless. This transmission protocol is block-oriented and analogous to T1, so we can use the same APDU features as those provided by the T1 protocol. Now, this particular reader provides quite a few configuration options that can be configured by sending pseudo APDUs, which are not forwarded to the card but are processed by the reader itself. For example, this APDU disables the timeout, making the reader wait indefinitely for a command response. It is also possible to configure the LED color and the buzzer because by default it makes a beep when a connection to a card is established. To summarize, since the APDU structure and the software communication interface are the same, we can use the same software, just that a contactless reader must be used. But with that, we conclude this lecture. Good luck with the homework.